Okay, let's start. Do you have any question you want me to go over? Even number, odd number from number 11, from this 11.7. 2, 11, 17, let me write it down. 2, 11, 17, 21, 35. Okay. Number 2, the series from 1 to infinity of 2n plus 1 to the n big over n to the 2n. I think see that this can be rewritten as 2n plus 1 over n squared to the n. So I think I will use root test. Okay, I will use root test. Number 7 and 30, 7 and 30 solution. The nth root of absolute of a sub n, that's the nth root of 2n plus 1 over n squared to the n. This is 2n plus 1 over n squared divided by n squared. Divide by n is good enough. So 2 plus 1 over n, this converges to 0. Right? Which is less than 1. So by root test, the series, but be explicit which series you're talking about, even though we have only one series here. I still want you to be explicit. This series is convergent. Okay, that's for numbers 2. Let's see number 7. Let me do it next door here. The series from 2 to infinity of 1 over n times square root of ln n. I think I will use integral tests. I think I will use the integral. But what is the reason, Thomas, you have integral test by just looking at that? Because of the following. Square root of ln x and x here. If I do substitution, right? Okay, if my u is ln x, then my du will be 1 over x dx. Is it right? So this will then becomes, later on, it will be du over square root of u. Does it make sense? From 2 to infinity. Okay, but by p integral p equals to 1/2, that integral will be divergent. Remember? Okay, that's why I have that in mind right away. Yeah, that's why I have that in mind right away.
You said that's divergent?
Yeah, that's divergent.
Oh, okay.
Yeah, that's divergent. Yeah, p integral will be convergent only when p greater than 1, right? Okay, so that's how I will argue. So the one I wrote in blue will be my scratch work. I will say let fx equals to 1 over x square root of ln x. Now fx is continuous. on 1 to infinity. Actually, you just need 2 to infinity here. The series starts from 2, right? Okay. And what else do we need? It's continuous, and Fn is equals to 1 over n square root of ln n, which is a sub n for n greater or equals to 2. The fact that it is decreasing, well, it is decreasing because n ln n is increasing. Okay, but it actually doesn't matter though, as long as the integral. We just talk about the integral. I will just talk about the integral right away. So basically fx is the continuous superposition function. Now then integral from 2 to infinity of 1 over x square root of ln x dx is equals to limit t goes to infinity of integral from 2 to t of dx over x square root of natural log of x. Then we do substitution, u equals to ln x, such that du is 1 over x dx, such that the substitution makes it limit t goes to infinity of ln integral from ln2 to ln t of du over square root of u. Okay, but this is divergent since it's p integral p equals to 1/2, which is less than 1. Okay, so the integral is divergent by p integral. The series, therefore, is divergent by what? By integral test, that's right. I think grammatically speaking, supposed to be by the integral test, huh? Well, anyway, I'm not teaching English here. Yeah, if I teach English, then I will be the first instructor who failed the class. That's for number 7, number 11. The infinite series from 1 to infinity of 1 over n cubed plus 1 over 3n. This is equals to this is equals to the series infinite series 1 over n cubed plus infinite series 1 over 3 to the n, right? Now, if you want to split the discussion, then you put a note here. Okay, you put a note here. Okay. 1 over n cubed is convergent by
Wouldn't that be P series?
P series, what is the P?
P is 3, which is
Mm-hmm.
greater than 1.
That's right. Okay. How about the other series? Why is the second series convergent? Let me rewrite it first so that you can see better. Let me rewrite it first. How about this? Do you see it better? What kind of series is that? Nobody knows.
Well, wouldn't you want to do that or rewrite that as a root test? I'm not sure.
No need. Actually,
Well,
no need.
what would the P series for that be?
Huh? This is
What
not
would the,
P. This is not P series.
Oh, I think I might have misunderstood you then.
This is geometric series.
Okay.
Right? The ratio is 1/3, which is less than 1. Okay, you can use root test also, but the root test will give you 1/3 right away. Right? But the thing is, like, for us to do root test, I need to show that a lot of work. But this one is clear. That's supposed to be clear. This geometric series. Remember, geometric series actually have the pattern of exponential function. Okay. Okay. Now, since maybe I put it this way, this guy and this guy are convergent, then the sum is also convergent. The sum of series equals to the series of sum only if they are convergent, by the way. If one of them is not convergent, then the whole part is not convergent. The whole series is not convergent. That's for number 11. Number 17. Let me do it here. Try to save some space. Number 17. Oh, shoot. This is the series from 1 to infinity of 1 over 2, 1 to 1, 3, 5, all the way to 2n minus 1. And then 2, 5, 8, 3n minus 1. Let me see this first. Like 3/5 compared to 2/3. That's greater, huh? No, less than 2/3. I will rewrite it this way. So this series is equals to solution. This series is equal to 1/2 times 3/5 times 5/8 all the way to 2n minus 1 over 3n minus 1. And I want to say that 2n minus 1 over 3n minus 1 is less than 2/3 for n greater equals to 1. But I need to claim this and prove. How to prove that? How to prove that's true? Well, when n is greater than 1 means 3n is greater than 3n minus 1 is positive, okay? We just need that to be positive so that I can cross multiply. Which is true. In other words, because this is true and they have if and only if relationship, then this is true. Now, once I'm done with that, then I can say, so that series 1/2, 3/5, 5/8, all the way to 2n minus 1 over 3n minus 1 must be less than equals to the series 2/3 times 2/3 times 2/3 all the way to 2/3, which is 2/3 to the n. Is it right? Now, but this series here is convergent by
Would that be by comparison test?
comparison. No. By comparison tests later on.
Oh
by,
wait, or is it by the
yeah, why is this?
geometric?
That's right.
Geometric,
That's
yeah.
right. So that series is convergent by geometric, where dr is 2/3, which is less than 1. Actually, I need to use absolute sign somewhere here. Okay, so by comparison test, Okay, this series, actually I'm missing one little detail that I'm supposed to write since the beginning. I need to emphasize that the sequence, the terms is positive. Right? I need to show that this is positive. Okay. Otherwise, I cannot use comparison theorem. Comparison theorem only works when the terms are positive or non-negative, to be more precise. That's for number 17. Number 21. The series of from 1 to infinity, -1 to the n of cosine 1 over n squared. This is alternating series. With the positive part to be cosine 1 over n squared, but this is convergent to 1, right? Which is not 0. Is it right? When n goes to infinity,
Yeah.
Cosine 0 is not 0, right? It's 1. So it's not decreasing. It doesn't matter decreasing or not, but it's not convergent to 0. So from there we say right away it is divergent. So the series is divergent. Give me a second. Let me say the reason first. Okay. Then that's number 21, number 30. The series, oh shoot, they use J here. Okay. But that J actually behaves like an N. Square root of J over J plus 5. That's alternating. It is an alternating series with the positive part Bj to be square root of J over J plus 5. This is J to the power of 1/2 over J plus 5 over J to over plus 5, sorry. And this is equals to 1 over J to the power of 1/2 plus 5 over J to the power of 1/2. Now, if J goes to infinity, this goes to 0. Right? Now, make sure this Bj here is the positive term though. So if the positive term converges to 0, then alternating series test it is zero. By alternating series test, this series convergent to 0. I supposed to also show that it is decreasing. So how to show that it is decreasing? Bj is decreasing. That's the claim. Why? Proof. So what happened here is you have proof inside proof. So inside a proof, you make a claim and then you prove that claim separately. Okay, so how do we prove this?
Would you want to change that into a function?
Do I want to change it to a function and do the
Or like,
derivative?
yeah.
I think that should work. I think that should work. The way I see is, yeah, we can. Yeah, so let fx equals to square root of x over x plus 5. We just want to show decreasing, right? So we can just do the derivative right away. So f prime x equals to the denominator always positive. The derivative will be, that will be 1 over 2 radical x times x plus 5 minus square root of x times 1. That is 1/2 square root of x plus 5 over 2 square root of x minus square root of x. This is 5 over 2 square root of x minus square root of x over 2. Let me give myself more space. Then I want to say that 5 over 2 square root of x minus square root of x over 2 is negative when and x is positive, so this is 10 less than 2x. That is for x greater than 5. Okay, so to be more precise, the terms actually eventually decreasing. Okay, so I fill in the details there. The thing is, like, if you use a regular paper, you you cannot really do the insertion like what I do right now, right? So this sequence here, square root of j over j plus 5 is eventually decreasing. Now somewhere in between, I'm supposed to put a little note. That it is a continuous superposition function. Okay, that's for number 30, and finally number 35. Number 35. Oh, shoot. I don't know how to do this. I look at this, I don't know right away, but I know I'm not giving up right away. N to the 1 plus 1 over n. Let's see what's the problem with this. If I do ratio tests, in which I compare that with 1 over n, you see, notice that something cancels and we get 1 over n to the 1 over n, right? Oh no, this is actually, no, this is not ratio test. This is limit comparison test. I'm actually done. This is equals to 1. Is it right? I want to show that this is actually equals to 1. I mean, convergent to 1. Let me prove it. Proof. How can let a sub n equals to 1 over n to the 1 over n? So the natural log of a sub n will be negative 1 over n, natural log of n. You see, right? Oh, I need to do L'Hopital rule. Okay, so instead of doing that, natural log of y equals to x to the negative 1 over x. So limit x goes to infinity of natural log of y equals to limit x goes to infinity of 1 negative 1 over x ln x. This is negative limit x goes to infinity. I apply L'Hopital rule. On the top becomes 1 over x, at the bottom becomes 1. That's 0. But on the left hand side, that's natural log of limit x goes to infinity of y. So limit x goes to infinity of x to the power of negative 1 over x is equals to e to the 0, which is 1. So 1 over n to the 1 over n is convergent to 1. Okay, by limit comparison test, the series 1 over n to the 1 plus 1 over n is divergent. Okay, since the limit compares, because since the series here is divergent, Yeah, so what happened is this guy behave quite similar to this guy behave quite similar to 1 over n. Okay, when they go to infinity, they behave the same way. And limit comparison tests, you just need the limit to be positive. It doesn't have to be less than 1, right? Limit comparison test, you need the limit to be positive, finite. Positive and finite. Of course, fill in the details that the sequence is positive, right? The terms are positive. So you, okay, let me put it in more details then. Okay, note that let's call that a sub n 1 over n to the 1 plus 1 over n is positive for n greater equals to 1. Now consider Bn, which is 1 over n, which is also, of course, positive. A sub n over B sub n is equal to, maybe I do B sub n on the top. B sub n on the top, A sub n at the bottom. That is 1 over n, big over 1 over n to the 1 plus 1 over n. This is equals n to the 1 plus 1 over n, big over n. But this is n to the 1 over n, right? Now I want to claim that n to the 1 over n is convergent to 1. Proof. Let fx to be x to the power of 1 over x. Notice that fx is positive. Okay. So then natural log of y is 1 over x natural log of x. When I apply limit, so I basically copy whatever I did on my Scratch work on the right-hand side, the one I wrote in blue. So then the reason I make it fx because I want to use L'Hopital rule. Which is equals to 0. But on the left-hand side, we have natural log of limit. Limit of natural log is natural log of limit. So limit of x approaching goes to infinity of y, which is x to the power of 1 over x, is equals to e to the 0, which is 1. By continuous superposition function, then n to the 1 over n converges to 1. See, I forgot a little detail. So, since the A sub n or the B sub n, I forgot which one, basically the harmonic one, then by limit comparison test, this series is also divergent. Okay, that's question number 35. Now, let me work on number 38. Actually, I have my lunch and then I think about it. Oh, you know what? Yeah, this is what I will do. Okay, why number 38 was difficult for me? Actually, I was thinking about this since Monday at the end of the class. I don't think about it for like all the time continuously, intermittently to be more precise. After the class on Monday, I spent like around 15 minutes to do that. I didn't get a clue. No clue at all. No clue at all at that time. And earlier today when I say, oh, think about what problem you want to ask me, but we will do it. I plan to do this together with you at the end, but at that time when I wrote it down, I didn't know how to do that yet. Okay, now let me tell you why I was confused. And then how, through my confusion, I realized, hey, you know what? I can do it this way. Here's the thing. So I make it in blue. This is not my formal work. This is what I try to do. Okay. Now what happened was this. I somehow think, see, this is convergent to 1. Right? This is convergent to 1. So 1 minus 1, the whole thing will be convergent to 0. So it seems like it's convergent, but no. The series of a sequence cannot be decided if it is convergent or divergent simply because the series goes to 0. No. If the series goes to 0, it doesn't imply this. I'm sorry, if the sequence goes to 0, doesn't imply the series convergent. No, it doesn't. We have counter example 1 over n, the harmonic series, right? Harmonic series, the sequence goes to 0, but the series goes to infinity, right? Okay, so I tried to solve this before. I tried to solve it, and of course, at the same time, I tried to be reasonable within the scope of our lesson. So the way I think is this. Okay, this is 2 to the power of 1 over n minus 1. I want to say that this is actually greater than 1 over n. Because if it is true, if this were true, okay, if this were true, which is not, then it is straightforward, right? This is divergent, then a series that is whose terms are greater than 1 over n must be divergent also. Okay, so I try to reverse engineer that, and I say, well, okay, let's prove that this is true. If this were true, then this must be true. Then this must be true. Is it right? Now the thing is, it is not. Actually, it is not. This is not true. So I was like, hey, man, if this works, that would be great. But see, when n equals to 1, they're equal. When n equals to 2 is 1 over 1/2 squared. But this is 1.5 squared, that's 2.25. It's already greater than 2. Okay, in other words, this inequality here fails when, even when n equals to 1. Okay, even when n equals to 1. In other words, the right-hand side is larger. In fact, if you take n goes to infinity, if you remember, this is actually converges to e, which is greater than 2. Okay, which is greater than 2. And then I say, okay, so maybe not this one, maybe not this one. Maybe not compare to 1 over n. Let's compare to 1 over 2n. Is this inequality true? And yes, actually, this is true. But the problem is how to prove that this is true. Why is this true? The limit is true though. 1 plus 1 over 2n to the n. This is convergent to e to the power of 1/2. Okay, even though for you, it is still question mark, right? For me, I happen to know it. I mean, I can work it out for you. Why it's true that this is 1 plus, this guy is equal to 1 over 2n to the power of 2n over 2, right? But I can block it this way. When n goes to infinity, this goes to e, right? Now, e to the 1/2, that's actually square root of e. That's less than 2. That's less than 2. So it seems to be okay at the limit n goes to infinity. Okay, so I have some hope that, hey, you know what? This is true for some n. I can tell it is true when n equals to 1, when n equals to 2. Do I need to prove that it is true for all n? There will be too much to explain to my students. Okay, but at least at this point, I know one thing, that 2 to the power of 1 over n minus 1 is bounded above by 1 over n, but bounded below by 1 over 2n. Is it right? Again, this is an inequality that I don't know how to explain to you in short and effective way. Can you follow me so far, my confusion? My confusion is not about I don't know how to do it. It's more about how do I explain it to my students. You know, I know a lot more inequality compared to you, right? But when you see this problem in your test, okay, what will you do? I mean, I cannot tell you all the inequalities that you need to know. I mean, can we just go back to the book, you know? Like if we base from the book, Thomas, then can we do this problem just based from what we learned so far without anything new? At least not too much new. Okay, so here's the thing. When I look back to this, I keep on, for this couple hours, I mean, intermittently, couple days, I keep on thinking, how do I explain this to you? Okay, how do I explain that this inequality is true? Because once I can explain this inequality is true, then we get this. And notice that this series here is bounded below by this series, which I can factorial 1/2. And this is harmonic, therefore it's divergent. Right? Bounded below by something divergent and positive terms. Right? But still, how do I prove this to you? That's difficult. That's difficult. I mean, I don't think my students have enough time if I actually throw this question in your test. Right? So how do I do that? And then I look at that, it's like, hey, hold on. It's bounded below by this, but bounded above by this. So at the infinity, the ratio 2 to the 1 over n minus 1 over 1 over n will be bounded above by 1, bounded below by 1/2. Right? Does it make sense? So when I pull this to infinity, when n goes to infinity, when I pull this to infinity, this will be a finite number. This will be a finite number. Therefore, by limit comparison test, the convergence of this must be the same to the convergence of this. That's what I will do now. Okay? That's what I will do. So what I will do is let solution, let a sub n will be the nth root of 2 minus 1. B sub n is 1 over n. Now, if you ask me, Thomas, how do you get that 1 over n? That's the background. That's the reason behind it. Okay, the one I did in blue. Now, comparing to 1 over n is not something out of nowhere, though. We did that before, right? It's just like, why you compare to 1 over n? That's the background. What if I don't know that that's the background? Just try to do with 1 over n anyway, okay? So a sub n over b sub n will be 2 to the power of 1 over n minus 1 over 1 over n. Now you will see that this actually works for every constant. It doesn't have, it has to be 2. It doesn't have to be 2. It can be anything. I remember like around 2 years ago, 3 years ago, I tried to do this problem at home, at school, and I think I actually solved that, but then I kind of like wonder, I didn't do it this way, I believe. I did it with much lower, longer method. After all, that's number 38, right? So it's supposed to be difficult. And I asked students, can you take a look on either the solution manual or what's that? I forgot the name. The name of the website where you can see the solutions. Slater, yeah, Slater. And then Slater gives the solutions kind of like, it's, I remember, also longer than this. This is the simplest one I can get. Well, anyway, so I will find the limit of this. And I want to claim that this will go to some finite number k. Okay, let's do it. Let's do it. Now, consider fx equal to 2 to the power of 1 over x minus 1 big over 1 over x. Okay, that's our y, right? Then limit x goes to infinity of y equals to limit x goes to infinity of this. Now notice that on the top and the bottom, both of them goes to 0. Okay. In fact, I can say it this way. This is limit t, or 1 over, if x goes to infinity, then 1 over x goes to 0 positive. Is it right? Then from here, if you want to do L'Hopital rule, go for it. If you want to do L'Hopital rule, go for it. But I think that's not what I will do. What I will do instead is to say that this is actually the first derivative of gt at 0 for gt equals to 2 to the t. Okay, now this is a big one. We learned this before. Okay, actually, when I say yes, I found out I could do it already. I didn't do it that way. Earlier, what I have in mind is from here you apply L'Hopital rule. So what I had in mind is from here you apply L'Hopital rule. You see what I mean? Okay, when you apply L'Hopital rule, then you will have 2 to the power of 1 over x times ln 2 times negative 1 over x squared. While at the bottom you have negative 1 over x squared, which cancels, get the boom. This is negative ln 2 negative, oh no, it's positive. Ln 2 limit x goes to infinity of 2 to the power of 1 over x, but that's equals to 1, right? This is ln 2 times 2 to the 0. You see what I mean? Okay, that's what I had in mind when I say now I can do it. When I wrote this down, then I realized, hey, you know what? By definition, this is actually the derivative of 2 to the t, or 2 to the x, if you want to call that, or 2 to the whatever, at 0. Okay, so I can change gear. After I write it down, then I can see I can do it even more simpler. So the derivative of gt is 2 to the t times ln 2. G prime 0 is ln 2. Okay, so by continuous superposition function, A sub n over B sub n is convergent to ln 2, which is finite and positive. Okay, therefore, by limit comparison tests, that series is divergent since this series is divergent by harmonic. See, I compared that to the harmonic series, right? I compared it to harmonic series. The limit comparison test shows that the limit is positive finite. Okay, so I'm done. I would really like to see how Slater actually doing this. As I remember years ago when I asked students did that, they show me something quite longer than this. I don't know if there's another one. They start similar? Okay, great. Yeah.
Yeah, they did a comparison to the same function.
Well, at least then, I remember 2 years ago, it's not. It's something totally different. So somebody might have come up with something newer. Or
there's 3 answers on there. That's the top one.
Oh yeah, this is the top one. The thing is like how did you know to compare to these? That's actually the biggest problem. Do we know to compare to this? Okay, and that's because of the long struggle I have from 2 nights ago. Yeah, intermittently, it's not like something I do all the time. When I took shower, then I think about it a little bit. I try to bound it below by something, but when I am able to bound it below by something, I still have to explain why I bound it below by that thing. You know, so can I explain this to you with the shortest path? And well, compared to this, if you ask me why, just do it. Right? But if you ask me the background why, then you compare to that. I try to mimic, again, I try to mimic this. Square root n root of 2 minus 1 must be bounded above or below by something. Okay, but let's call that thing question mark. If I reverse engineer that, I will get something looks like this. Okay. In other words, if it is finite, then I should come up with something whose series is finite here. You see what I mean? Okay, but the expression that I know that have this form only when we have 1 over n, or to be more precise, b over n, which I know is convergent to e to the b. That's what I try to use.
Yeah, the third answer on Slater sort of does that. They compare to, they say e to the x is greater than 1 plus x.
Now that's actually still e to the x is greater than 1 plus x. That's still a question though. That is still a question. How do we know that's true?
Right, yeah, they don't prove that. They just suppose that and then they solve it from there.
I can easily claim that it is true by looking at the graph. Right? I can claim that if you look at the graph, it is true. That's e to the x. This is 1 plus x. Right? But still, you can claim this thing, but how students will come up with that, it's still an issue. Once we are done with, I think 11.9, then this is explainable. I mean, we can, there will be something in 11.9 that shows us that this is actually e to the x is equals to 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24 and so on and so forth. That's Maclaurin series. Okay, therefore, if you truncate that, of course, e to the x must be greater than 1 plus x. Okay, but I cannot use the later material to explain the current material. I cannot use a PhD material to explain what you do in calculus 2 here, right? Okay, I'm exaggerating. I'm not saying that this is PhD material. I basically cannot use the later section to explain the current section. So even when I use this, it's still problematic. If you think about it, this is basically the same to say 1 over n is this, right? Do you see what I mean? But this is not true. This is true. This is true. This is not true. But what is so special with E? You will look at 2 there. You are not looking at E. Why suddenly you compare that with E? See, that's the issue. Okay, so it really took me some time to know what do I need to compare that with. You know, in fact, no, I didn't. I tried to do comparison tests, and it turns out that I end up doing limit comparison tests. Yeah, so I try to catch, is it bounded above or below? What is this guy supposed to be so that I can bound it above or below, so on and so forth. You know, and nothing works, nothing works. And then I realized, hey, you know what? I was even to the point of thinking like, should I compare that with 1 over 2n? But then when I think about it, hey, hold on, limit comparison tests, as long as this guy goes to a finite number, I'm safe. I don't need that to be less than 1. See, I myself at times still got confused with between ratio test and limit comparison test. You know, okay. Well, anyway, like what I said before, in the past, I have solution manual when I first start Calculus 3 class. I don't really use solution manual, but I would like to have them to be handy just in case. And yes, to be honest with you, there were 3 times, 4 times, up to 10 times. Not, I don't even think 10 times that I opened the solution manual. But when I open it, I just try to see if I really get it right. You know, I'm not someone who too proud, so proud to show that I cannot do a problem. If I cannot do it, I cannot do it. You know, so what's the big deal, right? Okay, I think it's more important that how do we come up with that idea on how to do this? Okay, so when I answer this question, okay, now you see that I compare with this, which happens to be, you say that the same to what Slater's doing, right? Okay, but still, even in Slater, I don't think that they explain or they have enough time to explain why you compare it with that. That's still a question mark. Okay, and what I explained earlier was the background. Okay, I compare that with 1 over n, doesn't work. I compare that to 1 over 2n, it works, but I have hard time to explain it. You know. Okay. Now the thing is, as a student, will you know to compare it with that one still, right? So it's not easy to be a teacher, okay? Because not only I need to know how to do it, I need to know it at your level. I need to know how to explain it at your level. Okay, that's for 11.7. I think that's all.
Somebody commented in the thing and asked him why he substituted that, and here was the guy's response.
Okay, yeah. It's not, it's later. It's in writing anyway. Hold on, I get somebody. Okay, I see Matthew's doing this. First thing I did was to write 2 as 2. Okay, that's what I have also in mind. And then write the limit goes to 0, it's 0. And go around the market looking for a function that has 0 limit. And a finite derivative at 0. I found that 1 over x satisfy both conditions. Oh, you copy paste that from Slater. Thank you. Okay. I go around the market. I like that term. See, if you go around the market, you will have too many functions. Well, anyway, anyway, I think I have to say that I'm lucky that when I have my lunch, my dinner, and that 5-10 minutes between classes, that I happen to say, oh yeah, I can do it this way. In fact, I didn't finish. I didn't really I didn't really take my dinner though. I just barely like, oh, you know what? I need to hit this up, and then while at the same time I write something on paper, and I say, oh, you know what? I think I can do it this way. Well, anyway, that's 11.8, 11.7, 11.8 power series. You don't know how much satisfaction I feel when I have a problem that I know I cannot do for a long time, or I kind of like trembling when I see that problem. Like this one, you know, since 2 days ago, I told you right away, number 38 is a problem I cannot do. I have that trauma, you know. I spend like at least half an hour to the point, maybe I think half an hour to 45 minutes in class. I cannot finish it. You know, I could not finish it. And then those students actually stay with me after class, and then we still discuss about that. I think we do it this way. I think we do it this way. I still cannot do it. You know, I have that trauma. Now I can do it. I even can explain why that's what I did, which is a great thing for me. Can I explain something in a simpler way that my students can understand? And I hope you do. Well, anyway, let's go on to 11.8. 11.8 to 11.10, basically a new material. This is basically a new material. 11.8 is on the easy side, 11.9 on the medium side, 11.10 is on a lot of memorization side. Okay, now let's start with a power series. What is a power series? Series is a power series if it has this pattern. It has this pattern. It is the infinite sum from degree 0 to infinity of c n x to the n with a convention that x to the 0 is equals to 1, even when x equals to 0. I mean, x to the 0 is always 1 except when x equals to 0, right? Okay, but the convention says that even with x equals to 0. Okay, so in our power series, x 0 to the 0 is considered to be 1. Now, basically, if you spell this out, this becomes C0 plus C1 for degree of 1, C2 is the coefficient for x squared, C3 for the coefficient of x cubed, so on and so forth. Okay, now that's what we call power series. Okay, now power series about x equals to a or around x equals to a has this pattern. X minus a to the n instead. So you see that you shift the x becomes x minus a. Okay, that's the power series. Now, the issue at hand that we want to do here is when will a power series be convergent? For what x? For a given power series, of course, it depends on the coefficients, right? Okay, but if we have certain coefficients for the power series, can we tell what will the x be so that the power series be convergent? Now, we have a theorem. I still assume that you watch my lecture video, okay? So I jump to the theorem. The theorem says the following, okay? Given a power series, there are 3 possibilities only. The first one, the series, it is convergent when x equals to a only. Which is always true. You know, if you think about this, if you think about this, C0 plus C1 times x minus a plus C2 times x minus a squared and on, then when x equals to a, then of course that will be, the series becomes C0 plus 0 plus 0 plus 0, which is just a constant term, right? Okay, so it must converge somewhere, at least at one point, okay, at the center. We also call this power series centered at A. Now, the second possibility, it is convergent everywhere for any x. Is it possible that you have a series, that a power series that converges everywhere? Yes, you will see that later on. Okay, now we will say, oh, let me do the third one first. The third possibility, it is convergent for some for the x minus a less than r for some r. Okay, and we will call this r radius of convergence. Now you will see that for part 1, then in this case, if it is convergent only at one point, then we say the radius of convergence is 0. If it is convergent everywhere, then the radius of convergence is infinity. Okay, so either the radius of convergence is 0, means it only converges at one point, x equals to a, or it is convergent everywhere, the radius of convergence is infinity, or the radius of convergence is a finite positive number. Now think about that. Why we call that radius of convergence? Let's say this is a, and we call that radius of convergence if you go r unit to the right and r unit to the left, it's convergent everywhere in between. But once it is outside of this, it will be divergent. Divergent here, divergence here. Okay, and still question mark, what happened with the endpoints of that radius of convergence, which we will check separately later on. Okay, now from radius of convergence, later on we will get interval of convergence. Okay, only 3 ways, only 3 ways. Now let's do problems. Let's do problems. So I hope through these exercises here, then you see how we get the radius of convergence and also interval of convergence. So let me do number 3. Number 3, the question is find r, that's the radius of convergence, and I, which is the interval of convergence. Okay, number 3, the series from 1 to infinity, -1 to the n times nx to the n. Not like before, we have only n, right? If you take a look on 11.7, right? We have only n, right? We have only n. We have only n. In this case, it's j. We have n, we have n, we have n. Now, the n is the counter. The x is the number you can replace there and still being convergent. Now, how to find the radius of convergence? What we will do is, what we may do, part of that is doing ratio tests. Okay, by ratio test, -1 to the n plus 1 times n plus 1 x to the n plus 1 over, remember ratio test, the next term divided by the current term. We use absolute value. One reason is to get rid of those negatives, the alternating. Okay, so we will get n plus 1 over n times x. Is it right? Which is equal to 1 plus 1 over n over 1 times x. This is convergent to, you know what? Let me still put the absolute sign because x may be negative. This goes to absolute of x. Now, do you remember when will the ratio test give us convergence result? When it is less than 1, right? Now, notice that this fits into the picture x minus a less than absolute of x minus a equals to r, where the a is 0, the r in this case is 1. Okay, what I want to say is this. When you see your radius of convergence, the coefficient of x has to be 1. It has to be x or x plus or x minus something. So if you see these, then the radius convergence is 5. Okay, if you see these, the radius of convergence is not 5. You have to make it x minus something less than 5/2. Therefore, the radius of convergence is 5/2. Okay, now anyway, let me come back. So the radius of convergence is equal to 1. Okay, that 1 comes from here. Okay, because the absolute of x minus a is what you see on the other side. Okay, now radius of convergence is 1. In other words, from there we say that if absolute of x less than 1, then x is between 1 and -1, right? Okay. X is for sure convergent in this interval. Now we want to see if it works at the endpoint. Now you check the endpoint. At x equals to 1, what happened to the series? When x equals to 1 and equals to 1 to infinity of -1 to the n times 1 to the n. This is just the infinite series. In fact, it is alternating, right? It is alternating with positive term n. Now notice that Bn is not convergent down to 0. Maybe let me say it's convergent to what? Bn, the positive term, n is convergent to infinity. That's divergent. So by alternating series tests, this series is divergent. In fact, using the same argument, oh, is it right? If we use the same argument, I tested. When x equals to -1, what happened? So once you get the interval of convergence from the radius of convergence, you still need to check the endpoints. Okay, you still need to check the endpoints. So this will be the infinite series -1 to the n times -1 to the n. But this is -1 to the 2n, which is always 1. Okay, the nth term goes to infinity. You see the same argument actually, right? So by test of divergence, this series is divergent. Now from there, then we know, so the interval of convergence is from -1 to 1, not including the endpoints. Think of it this way. From radius of convergence, you know that it will be convergent here. But we try to see if it is still convergent at the endpoint. At the endpoint. We want to see if it's still convergent at the endpoint. That's why we have that 2 extra things to check. Okay, that's for number 3. Let's see number 5. Let me erase this. After this number 5, I'll give myself a break. We have the series. It's still centered at origin though. X to the n over 2n plus -1 by ratio test. Multiply by the reciprocal. This will be absolute of x times 2n minus 1 over 2n plus 1. Okay, which is equal to absolute of x divided by n on the top, divided by n at the bottom. This goes to converges to x. Okay, but ratio test will be convergent if the ratio, absolute of ratio is less than 1. So we still have the radius of convergence is 1. And it is for sure convergent at x between -1 to 1. Now the question is what happened at the endpoint? So 1 over 2n plus 1, right? When x equals to 1, there will be 1 to the n, right? Which is always 1. How do you show that this is convergent? And try to think simple, because if you think hard, you have a longer proof, right? I will do it this way. This guy is greater equals to the infinite series 1 over 2n plus 2. What do you think? Okay, but that is, this series is divergent by harmonic. So by comparison test, this series is divergent. Is it 2n plus 1 or 2n minus 1? 2n minus 1. Oh, if it is 2n minus 1, then it is a lot easier. I don't need to do that. I'm sorry. I'm sorry. Ah, kill. I'm working too hard. 2n minus 1, 2n minus 1, 2n. This is divergent by harmonic. So by comparison test, minus 1 is divergent. Now what happens if the x is -1? The infinite series becomes -1 to the n over 2n plus minus 1, right? But this is an alternating series. With the positive term 1 over 2n minus 1, which is convergent to 0. Right? Decreasing, convergent to 0. So by alternating series test, this series is convergent. So the interval of convergence now is -1 including the endpoints, up to 1 not including the endpoints. Okay, now I will take a break until 9:15, and then I would like you to choose problems between, let's say, between number 9 to number 27 for us to do. Okay, let's take a break. Okay, let me try number 11. This is still centered at 0. We need to find the radius of convergence first. So the next term divided by the current term will be -3 to the n plus 1 times x to the n plus 1 over, let me make it this way, m plus 1 to the power of 3 halves times n to the power of 3 halves over -3 to the n x to the n. This will be -3x times n over n plus 1 to the power of 3 halves. Okay, so this will be absolute of 3x, absolute of, actually I don't need the absolute, that's positive number, n over n plus 1 to the power of 3 halves. You know what, let me just divide the top and the bottom by n right away. Okay, but this is convergent to absolute of 3x, 3 absolute of x. Now, when I set this to be less than 1, then we get absolute of x to be less than 1/3. So the radius of convergence is 1/3. And the interval for now is between -1/3 to 1/3. Now, check the endpoints. At x equals to 1/3, will that do the work? So the series -3 to the n times 1/3 to the n over n square root of n. This is equal to -1 to the n over n radical n, which is an alternating series with the positive term 1 over n square root of n, right? Okay, which is clearly that's decreasing, go down, convergent to 0. So by alternating series test, this series is convergent. What happened when x is -1/3? That is 1 to the n, which is 1, over n to the power of 3/2, right? Which is convergent by P series. P equals to 3/2, which is greater than 1. So now we can update our interval of convergence to be including -1/3 and including 1/3. Okay, from radius of convergence, we only get the radius 1/3, but we don't know yet about the endpoints, right? Now we update that after we test the endpoints, we update that it is convergent at including the endpoints. Okay, that's for number what? Number 11. Any problems you want me to go over? Otherwise, I choose the problems myself. I think I will do 2 more from here. Number 17. Oh, let me see. Any is fine. Okay. Let me do number 17. I don't know in my lecture video how many problems I did. As I remember, I usually do even numbers, so I choose odd numbers right now. So the series from 1 to infinity of 3 to the n, x plus 4 to the n over square root of n. Okay, so the absolute of the next term over the current term will be 3 to the n plus 1 times n plus x plus 4 to the n plus 1 over square root of n plus 1 times the reciprocal. So we will get 3x plus 4 times square root of n over n plus 1, right? So we will get 3 times absolute of x plus 4 square root of 1 over 1 plus 1 over n, which is convergent to 3 absolute of x plus 4. Now set this to be less than 1. So we get x plus 4 is less than 1/3. So the radius of convergence is 1/3, but this time it is centered at x plus 4. Okay, subtract by 4, subtract by 12, so that's negative 13 over 3. That's negative 11 over 3. Now then I check the endpoints. Three to the n, negative 11 over 3 plus 4 to the n over square root of n. That is equal to, that's 3 to the n times 1/3 to the n. Oh, that's the one. Which is divergent by P series, right? P equals to 1/2, which is less than 1. How about at x equals to negative 13 over 3? So n equals to 1 to infinity, 3 to the n times negative 13 over 3 plus 4 to the n over square root of n. That is the series 3 to the n, negative 1/3 to the n. Oh, that becomes alternating, huh? Is an alternating series with the positive term 1 over square root of n, which is decreasing and convergent to 0. So by alternating series test, this series is convergent. So now the interval of convergence will be including negative 13 over 3, but not including negative 11 over 3. That's number 17. Let me try number 23. Or maybe I have done number 23. Yeah, I do number 23. The series n factorial times 2x minus 1 to the n. I will do ratio test again, but don't forget, besides ratio test, we also have root test. And n plus 1 factorial times 2x minus 1 to the n plus 1 over n factorial 2x minus 1 to the n. This will be n plus 1 times absolute 2x minus 1. But this will go to infinity, right? When x is not equals to 1/2. It will go to 0 when x equals to 1/2. So this is the case when the radius of convergence is 0. It is convergent only at one point. Okay, and what point is that? When x equals to 1/2. Okay, so it is not the interval. The interval have radius 0. There's only a singleton. There's only one number that makes it convergent. It is when it is right at the center. Number 27, I hope this is the last one. Then from here, we can do problems with conceptual. Okay, number 30, number 32, maybe, okay. Number 27, the series of x to the n over 1 times 3 times 5 all the way to 2n minus 1. Actually, the one down here, I need to be careful. The next term after this is this one. Such that most of them cancel and I get x over 2n plus 1. Now, this will go to 0. As n goes to infinity for whatever x. So the radius of convergence will be, I mean, the ratio is always 0 when n goes to infinity, right? Which is, it means it will always be less than 1. Therefore, the radius of convergence is infinity. Interval of convergence is all real numbers. So these R here is for radius. This is for all real numbers. Okay, number 30, more conceptual problem. Number 30. Suppose that this series is convergent when x equals to -4, divergent when x equals to 6. Okay, so let's picture this. It is centered at 0, right? This is a power series centered at 0. Hey, what happened? It is a power series centered at x equals to 0. Now let's picture this first. At -4, it's still convergent. At +6, it's divergent. It means it is convergent. The radius of convergence is at least 4, right? It's convergent. up to 4. Okay, it is divergent if the radius is more than 6. You see what I mean? Okay, now we cannot say anything, nothing can be said here. Okay, nothing can be said between radius 4 from origin to radius 6. Now, so part A, what can be said about the series when x equals to 1? That's basically what happened, right? This is when x equals to 1. Is x equals to 1 in the blue part that is convergent? Yeah, so this is what happened here is the x is equals to 1, which is within -4 to 4, right? So it is convergent. Part B, what happened with 8? At 8. So the x is 8, which is not an element of -4 to 4. Actually, to be more precise, is in the red part. It is element of -infinity to -6 union 6 to infinity, right? So that will be divergent. We cannot say anything if the radius, the distance of that x from origin is between 4 to 6. But less than 4, it's convergent. Greater than 6, it must be divergent. Part C. How about the series -3 to the n? Well, the x is -3, which is element of the interval of convergence. So it must be convergent. Part D, we have -1 to the n, Cn 9 to the n. Now from there we see that x is -9, right? Which is element of the interval where it will be divergent. Okay, that's for number 30. Number 32, honestly, I don't know. Yeah, finding the intervals. Okay, maybe we do it later. Number 31, maybe. Oh, you know what? Yeah, let me do number 31 first. If k is a positive integer, find the radius of convergence of the series n equals to 0 to infinity n factorial to the k over k n factorial. Oh, I'm sorry, no, that's not correct. Kn inside factorial of x to the n. But k is an integer. Find the radius of convergence. K is positive integer. Okay, we need to do this. So that will be n plus 1 factorial to the k over k times n plus 1 factorial. Oh, wow, that's nasty. X to the n plus 1 times the reciprocal let's see, times x to the n. So I have absolute of x outside. Let me group them here and there first. So I have absolute of n plus 1 factorial over n factorial to the k. This is kn factorial. This will be, so this guy here will be kn plus k factorial. Kn plus k factorial. You see that? This will be absolute of x n plus 1 to the k. Ooh. This will be kn factorial over kn plus k, kn plus k minus 1, kn plus k minus 2, all the way to kn plus k plus 1 times kn factorial. So I get n plus 1 to the k on the top over to the k. It looks like multiplied by k. Let me bring it up further. And at the bottom, I have k times n plus 1. That's just for the first factor here. Okay, and then kn plus k minus 1 all the way to kn plus 1. I don't know. I think I will do it this way. So I break it even further. N plus 1 over k times n plus 1. N plus 1 over k times n plus 1 minus 1 over k. I wonder if it gets me anywhere. Oh, I see. Okay. No. I will not factor the k. Just leave it like that. Oh, then for each one of them, I divide the top and the bottom by n. I wonder if this will do though. Each of them actually convergent to 1 over k, right? This will be convergent to absolute of x over k. Oh, hold on. As n goes to infinity, that will be 0. The thing is, I have n terms here. N terms or k terms? K terms, okay. So absolute of x over k to the k. I want this to be less than 1. So absolute of x is less than k to the k. Ooh. Wait. That's number 31. Let me check the answer, okay? Somehow I have no confidence on this. Oh yeah, that's k to the k. Yay! So the radius of convergence is k to the k. Okay, that's for number 31. Number 32, you need to memorize some. What's that? Some function with some interval. Okay, number 37 first. Number 37, we have that series. Let fx equals to 1 plus 2x plus x squared plus 2x cubed, and so on and so forth. That is fx equals to the series from 0 to infinity of c and x to the n, where the cn equals to 1 when x is even, when n is even, 2 when n is odd. Find the interval of convergence of the series and find an explicit formula for fx. Oh, wow. I think I will break it up this way. I will make it like this then. I will make it like this. Let's say this is my first term. This is my second term, third term. Okay, so I rewrite it this way. Fx equals to fx is equals to the series from 0 to infinity of x to the n plus 2 times x to the, oh, hold on, it's every 2, huh? X to the 2n, 2x to the 2n plus 1. So let's check. When n equals to 0, I get x to the 0 plus 2x to the 1. When n equals to 1, I get x squared plus 2x cubed, right? So when n equals to 0, I get this. When n equals to 1, I get this. Okay, now you may wonder why I want to do that. That's basically, I create them as a piecewise defined series. Now then from here I split them. Let me pull the 2 out. This is x to the 2n plus 1. Column. This will make the radius 1 though for each one of them. But that's not true. When x equals to 1, it should not work. I don't think this is true. Let me be more careful. That's what I get. Still the same, huh? It's absolute of x squared. Set it less than 1. So x still between 1 to -1. Okay, I mean, if I'm sorry. I'm almost done, don't worry. Absolute of x being squared is less than 1 means absolute of x must be less than 1. So x must be between -1 to 1. The radius of convergence is 1. Can we find the explicit formula? I think then this is when I want to, I come from here. This is the series n equals to 0 to infinity of x squared to the n plus 2 times 2 times x squared to the n. Now, this is equal to, the first term is 1, the ratio is x squared. This guy, so this is from 0. The first term is 2x, the ratio is x squared. So this is equals to 1 plus 2x over 1 minus x squared. Oh, we can actually just look at that from here. When n equals to, the first term is 1 plus 2x, the ratio is 1 minus x squared. Duh, I'm thinking too hard. No need, this is not necessary. Yeah, because that's geometric functions, geometric series. Okay, I will stop here. Okay, your suggested homework, you know what to do. Okay, see you then on Monday. Then we will do 11.9. That's a pretty long section as I remember. Maybe not that long, but I would like to talk more. Then we may touch base a little bit on 11.10, but again, I'm not rushing. Okay, so Monday 11.9, Wednesday 11.10. Then we are done with this. Then we can start working on problems on the Monday, or maybe on next week, Wednesday, we start working on problems already. Okay, see you then.